Today, you'll be working on worksheet 1.1, page 7 in your workbook. That's graphing piecewise functions. So I'm just making this video example to guide you on how to graph piecewise functions. Remember, a piecewise function has a different definition for each section of the domain, different definition for each part of the domain. So we can really look at them as individual expressions or individual relations or individual functions, and then that will help us graph them better. Because I know you remember how to graph each of these types of graphs on their own, but when it's all put together, it can appear confusing or it can appear difficult. But if you split them out like this, then it helps you to graph them individually. So I've used these lines to show you what the different sections of the domain are and where that graph exists for each of these different definitions. So we're going to start with this one, y is equal to x out of 2 minus 5. This looks a lot like y equals mx plus b. And I hope you remember that m is the slope and b is the intercept, the y-intercept. Slope being rise over run. So if I want to graph y equals x minus 2 over 5, x out of 2 minus 5, I'll ask myself what's the slope from this equation. You can see the slope is 1 over 2 and the y-intercept is negative 5. So I'll go to my graph, find the y-intercept, negative 5, but keep in mind that that part of the graph, that part of the range does not exist in this section. And then I'm trying to use the slope. So if I use the slope, which is 1 out of 2, rise 1, run 2, conventionally I would have gone rise 1, run 2, so the next point would be there. But I can also go the other way, and instead of rise, I fall 1, and I still run to the other direction to find the next point. I can repeat that process because I'm only interested in values of the range that are in this section of the graph. So again, I will drop 1 and then run 2. Run 2 to find the next point, drop 1, run 2, find the next point, drop 1, run 2, find the next point, drop 1, find 2, like that. So I have those points on my graph, and I can draw the line of the graph, straight line, as straight as straight line can be. That's better. But yeah, yours shouldn't be shaded like mine. Yours should be a perfectly straight and beautiful line. There we go. Remember, this graph does not exist here. So I'll take this out. I'll take that out from there. And because x is less than negative 2, I know negative 2 is not included in the solution, so it will start with a circle right there to show that it's not included. Let's go to the next one. The next one is this right here. Let me do it in blue. This one, it's not blue. This section of the function, 2x minus 1. And for that section, let me remove this. For that section, again, y equals 2x minus 1. I hope you can see that the slope is 2 and the y-intercept is negative 1. Slope is 2, same thing as 2 over 1. So if I find the y-intercept, which is negative 1, negative 1 is right here, that graph is only existing in this portion of the range, or of the domain, sorry. So what I'm going to do is find the next point. The next point, if I did rise over run, I would have done rise 2, run 1, but it's not going to exist there. So I'll do it the other way around. Instead, I will fall 2 and run over 1. So the next point is going to be there. Then I can repeat the process, fall 2, go over 1. The next point would have been there. Connect them with a beautiful straight line. Wow. Okay, so that's that portion of the domain. The next one is this quadratic expression, which I will do in green. The quadratic expression, I can graph it two ways. I hope you remember, just do a little bit of review, that if you have y equals x squared, this graph is a graph that goes through the origin. And if you have y equals x squared plus 1, then that's the same exact graph, but it's just shifted 1 unit on the y-axis. And if it was y equals x squared minus 1, exact graph shifted 1 unit below the x-axis. Now, if it's y equals x plus 1 squared, it is shifted still, but instead of being shifted along the y-axis, it's shifted along the x-axis. So instead of having started here, if it was just x squared, it will this time start here at the point -1. I hope you remember this. It's just a small reminder. And if it was x minus 1, it would be shifted 1 unit to the right, which would start here at 1. So with that in mind, again, I can either graph it like that, or I can just simply substitute the values. So with that in mind, x minus 2 squared minus 1, if I want to go the easy way of substituting the values, I can plug in 0 in that function and see what y is when I plug in 0. So when I plug in 0 for x, I'll have 0 minus 2 squared minus 1, which will give me 3. So I know that when x is 0, right here, the y value is 3, right? And I also know, I can plug in another value. So after 0, I have 1, 2, 3, 4. So after 0, I can plug in another value. Let me plug in 2 because I don't want to do so many. If I plug in 2, I'll have 2 minus 2 squared minus 1, which is -1. So when x is 2, y is -1. That's right here. And let me plug in something else. If I plug in 4, let me plug in 4. I'll be 4 minus 2 squared minus 1, which is 2 squared minus 1, which is still 3. If I plug in 4, the value is still 3. I hope you can see from this little review that we were doing here that y equals x minus 2 squared minus 1. This means it's shifted 2 units on the x-axis, and this means it's shifted 1 unit on the y-axis, 1 unit down. And when you look at the graph that it's going to come out to be, it's really the same exact thing, because it's a terrible curve. That's better, maybe. Because when you look at the graph, it was shifted 2 units from here, 1, 2. So this is where it's starting, and it shifted 1 unit down, which is still 1. So you can graph it that way, or you can go the old-fashioned way and plug in numbers. Now that's what the function looks like in that region. And in the last region, I will use yellow. The last region is still a linear function, and you guys must be enjoying to graph linear functions because they are the easier ones. It's a linear function that's defined as y equals 2 minus x out of 2. The slope, I hope you can see that, is -1 out of 2, and the y-intercept is 2. So find the y-intercept, that is 2. 2 is right here. But keep in mind that this part of the graph, I'm only interested in the graph existing in this section, only that section. So whatever I do on the other side, I will take out. So y-intercept is 2, that's right here. The slope is -1 out of 2, so that means 4, 1, and then run 2, right? Because it's -1. So the next point would be here. If I repeat that process, 4, 1, run 2, next point is here. 4, 1, run 2, next point is right there. 4, 1, run 2. So already I'm in the region that I'm interested in. Now you can ask me, how do I just start from where I want, or from the section of the domain that the graph is in? If you want to just do that, since you can see that what this line is at 4, and this curve is only existing for x greater than 4, I can just plug in x equals 4. When I plug x equals 4 in this function, I will get a y value of, what do you guys think? Put here 4 divided by 2 is 2, y value is going to be 0. Good job. So if I plug in x equals 4, y value will be 0, and that's this point. And then I can start from this point to find the next point in this part of the domain. And I'm just going to use the slope by dropping 1, running 2, dropping 1, running 2, dropping 1, running 2, as many of those as I want. Then I can draw my function. Not to forget that since it's greater than 4, it starts off here with a little circle to show that that point 4 is not included for that section of the graph. So this is your piecewise function that we've graphed together. And I also graphed it with Desmos just to compare how good I am at drawing, and this is what it looks like. So I hope this helps. If you have any questions, please send a message, send an email, and then we'll help you. Bye.